This question says, suppose a 500 milliliter flask is filled with 0.7 moles of CO, 1.1 moles of water, and 0.5 moles of hydrogen. The following reaction becomes possible. We have carbon monoxide plus water yields CO2 plus hydrogen. The equilibrium constant K for this reaction is 0.274 at the temperature of the flask. And it says calculate the equilibrium molarity of carbon dioxide. Round your answer to decimal places. So this is a very challenging problem. And if you haven't watched the previous video on the playlist where we talk about setting up ice tables, I strongly recommend you do that before watching this video, because we're going to need to use the ice table here and then actually do the math to calculate the value of X and in turn the concentration of CO2. So first I want to set up the ice table. So the ice is the initial, which is going to be in molarity, the change, and the equilibrium concentrations. And I need the concentrations of everything. So first my reactants, carbon monoxide and water, and also my products, carbon monoxide and water, and my products are carbon dioxide and hydrogen. Now I need to find the initial concentrations of each of these things. Unfortunately, I'm given these in moles, not in molarities. So in each case, I need to divide by the volume, which is 500 milliliters or half of a liter, which makes this 1.4 molar. For water, I divide again by half a liter, which makes it 2.2 molar. And same for hydrogen, divided by the half a liter, which makes it 1.0 molar. So now I've converted all these to molarities. So my initial concentration of CO, I'm going to drop the molarity. I'm just going to put it in as 1.4. I put the molarity over here. The water, I'm going to put in as 2.2. Carbon dioxide, I'm not given an initial concentration of, so we have to assume that that's 0. There isn't any of it because we didn't put any in the flask. And then finally for hydrogen, it's 1.0 molar. Now, we need to look at the change. Well, this reaction is going to proceed to form carbon dioxide. So the change is going to be to lose a CO, lose a water, gain a carbon dioxide, and gain a hydrogen. Since the stoichiometric coefficients here are all 1, I'm going to lose, that should be minus X, lose 1 carbon monoxide, lose 1 water, again they're both 1 because the stoichiometric coefficients are 1. I'm going to gain a carbon dioxide, and I'm going to gain a hydrogen. So at equilibrium, the concentration of CO will be 1.4 molar minus the molarity I lost. For water, it'll be 2.2 molar minus the X again. For carbon dioxide, it's 0 plus X, or just X. And for hydrogen, it's 1.0 plus X. So this is my ice table. And this is about where we got in the previous video. But here we need to take this a step further, and we actually need to calculate the value of X, which is a quite tedious job. So remember that equilibrium, K, is equal to products over reactants. So it's the concentration of CO2 to the 1, because it's 1, stoichiometric coefficient is 1. Concentration of hydrogen, again to the 1, divided by the concentration of CO to the 1, and the concentration of H2O, again to the 1. Remember, if there's a stoichiometric coefficient of 2 here, you would have to square this. In this case, that's not necessary. So this is equal to my equilibrium constant. Now, K is given. These equilibrium concentrations are all given in terms of X. We can plug in. So K, which is 0.274, equals concentration of CO2, which is X, concentration of hydrogen, which is 1.0 plus X, divided by the concentration of CO, which is 1.4, I don't know why I put the molar there, 1.4 minus X, times the concentration of water, which is 2.2 minus X. So now I have plugged in my X values and for my equilibrium concentrations on the ice table. So these are the values for the concentrations in terms of X. We now have to solve for X. So in this case, 0.27, whoops, that's not, let me write that again, 0.274 equals, I want to distribute the x through this equation. So x times this is 1.0x, or just 1x, plus x times this, x times x is x squared, so plus x squared. In the bottom case, however, I have to actually FOIL this. So first times first is 1.4 times 2.2, which is 3.08. Now I need to do the inside, which is minus 1.4x. Excuse me, the inside would be minus 2.2x, plus the outside, minus 1.4x. So this times this, and this times this, and add them together, and you get minus 3.6x. So that's, for the inside, minus 2.2x, minus, well, actually plus negative 1.4 times minus x, which is plus negative 1.4x, which gives us the minus 3.6x. Then finally the last, minus x times minus x, which is plus x squared. So that gives me the equation so far. I now need to move the sheet up. So now I need to further simplify by cross multiplying. So I need to distribute the 0.274 through all of these numbers. So 0.274 times 3.08 is equal to 0.844. 0.274 times minus 3.6 is equal to minus 1.9864. The x stays. And then 0.274 times x squared is just plus 0.274 x squared equals, this is over 1, so when you cross multiply you just get the same thing, 1.0x plus x squared. Now, in order to use the quadratic equation, we need to set this thing equal to 0. There are multiple ways to do this, but what I'm going to suggest we do is we subtract 1.0x from the x term, minus 1.0x, and we subtract x squared from the x squared term, minus x squared. That will get rid of these, and this will be equal to 0. When we do that, we get 0.844 minus I have to apologize, I made a mistake here. When we multiplied this through, the minus 3.6 times the 0.274, it was actually 0.9864x, not 1.9864x. It's not until we subtract the 1x that we get minus 1.9864x, and then 0.274 minus x squared is equal to negative 0.726x squared, and now this is all equal to 0. So we have this now equal to 0. Now I'm going to write this the more traditional way, so we have ax squared plus bx plus c. So I'm just going to pull this out as minus 0.726x squared minus 1.9864x plus 0.844 equals 0. And if you would prefer that these numbers are positive, you can multiply through by negative 1, make this positive, and this negative. You'll get the exact same answer, and it'll still be equal to 0 because 0 times minus 1 is still 0. So now I have ax squared plus bx plus c, and I can use the quadratic equation. So again, ax squared plus bx plus c, and I can use the quadratic equation to solve this. So the quadratic equation is x equals negative b plus or minus square root of b squared minus 4ac all over 2a. And we're going to get two answers. We're going to get the answer when we add, and we're going to get the answer when we subtract. So in this case, x equals negative b, okay, which is the negative of the negative. so it's negative 1 times this negative number, so it's 1.9864 plus or minus square root of b squared, which is minus 1.9864 squared, minus 4 times a, minus 0.726, times c, which is 0.844. All divided by 2a, 2 times minus 0.726. Now, when you do the plus of this, you get negative 0, when you do the plus, you get negative 3.1099. When you do the minus, you get 0.3738. If we go back to our original table, way up here, we find that one of the values is 1 plus x. And in this case, if the value is negative 3.1099, this will be negative 2.1099. You can't have a negative concentration. So this value of x is not valid because it would lead to a negative concentration in the case of both hydrogen and in the case of carbon dioxide. You would have a negative concentration, and that doesn't make any sense. So this must be the value of x. And again, we solved the quadratic equation twice. We get two values, but only one of them makes sense. So this is the value of x. Now the original question says, calculate the equilibrium molarity of CO2. Well, we found that x equals 0.3738. In this case, the equilibrium value of CO2 is simply x. So at equilibrium, the concentration of CO2 equals 0.3726 molar. So that is the answer. Note that if we were asked for the equilibrium concentration of hydrogen, we'd have to add 1 to that, and it would be 1.37 molar would be the equilibrium concentration of hydrogen. And if we were asked for the equilibrium concentration of water, we'd have to take 2.2 minus the 0.37 molar. So you would have to actually solve it in. The only reason it's exactly equal to x is because the equilibrium concentration of CO2 is equal to x. So this question is a ton of work, and basically it's very important that you solve through all of this so you have some practice doing it, and maybe you remember some stuff you learned in math class a long time ago, which can be pretty helpful. I know setting up for this video I had to review using the quadratic equation.